Welcome to Everything Distributed. Today we are going to talk about transactions. And the material is based on the chapter 7 in Martin's book. So far we have talked about lots of different read and write operation, including like consensus and then replications and their usage. And for those, we only focus on two very simple primitive, read and write. So that's also where we also call it that read-write data object. And today, we are going to talk about the more complicated operation, but like it's much more useful. And then the notion of its transaction. So it's that you have a beginning of transactions, and then you will do something that's interacting with the database. For example, read lots of different objects and write different objects, and then those can touch different keys or different kind of data objects. And then in the end, you just say that end, my transaction terminates. And why is it so powerful? It's because that the idea of transaction or this abstraction is that everything you do inside this begin transaction and end transaction is a logical and then the unit of work, and then this unit of work is actually unbreakable. And then that's the original idea, the concept for transaction. And then there are only two outcomes. The first one is commit, meaning that your transaction is completed and it's kind of affected or successfully update the state of your database. And or you have abort, meaning that the transaction cannot be completed and then it has to abort and then kind of roll back to the previous state. Okay. So it's a different from the notion of read and write, because there we want it that they are always able to succeed. But like for transaction, it's possible that the database decide to abort your transaction. And then as an application developer or as a user, after you see a abort, you can always do a retry or like doing something else. So one classical example for transaction is that suppose I have two bank account, one is A and then the other is B. And suppose A wants to transfer $3 to B's account. And then in terms of logic or like how you are going to implement it, it's very simple. You have A's account and then you say, I'm going to reduce $3 from it. And then I just add $3 to B's account. And then that's it. And that's the notion of transaction. And then if you are familiar with a SQL kind of semantics, this is how you are going to do it. First, you have this update semantics, and then you are going to say that the key is A's account. And then this set tells you that how to update the state of A's account. So what you do is that the balance is equal to balance minus 3. So that's equivalent to this English meaning, reduce $3 from A's account and then add $3 is similar. The only change is here. You are going to add $3. Okay. Then in terms of like transaction here, the notion is that you begin transaction and then you say reduce $3 and add $3 and end transaction. And then our outcome is that if it commits, meaning that the transfer is complete, or abort, meaning that nothing happens. Okay. And then one very important notion here is that this transaction should be an unbreakable unit of work, meaning that it's atomic operation. And this is particularly important if you want to implement this kind of a bank account, right? So in this case, if it's not unbreakable, so it's possible that, okay, this thing is completed, but that this thing is not completed, then what would happen is that $3 just missing. And then nobody gets that $3 because you already subtract that or reduce that $3 from A's account, but like B doesn't get it. Then this is not a good application because that something is missing. right? So that's why that we want to define this transaction as a single logic unit, and then it should be unbreakable. Okay. And now let's look at the state diagram of a transaction. It's this object. So there are several states. The first one is that it's active, meaning that, okay, begin the transaction. Then begin transaction, remember there are lots of small operation inside the transaction. So if like some operation is like kind of committed or executed, then it will become to partially committed. So if you remember the previous example, if that A's account has already been subtracted, you go to this partially committed part. Then if at any point of time you receive any kind of failure, then you should go to the fail state. So it's possible that you find something like inconsistent or that you find some error, then the database should go to the fail state. Then if you whenever you enter the fail state, you should try to abort the transaction. Or if everything is committed, then you should go to the commit state. Okay. Then after this, if it's committed, then that means that transaction can be terminated. And if it's aborted, that also means the transaction can be terminated. So that's the whole life cycle of the transaction. You start from active state, you keep like doing the operations, and then if everything succeed, you go to the commit, and then you terminate the transaction. This is the NTX in the previous example. And if it's something went wrong, then you should go to the fatal state and abort the transaction. Okay. Then the next one is that what happens if I abort the transaction? Then the notion of recovery is that I should roll back all the partially committed operations and then to the previous commit point. So the idea of the commit is that it's always in a good state. So that if I cannot commit my current transaction, then I should roll back to the previous commit. And then in terms of transaction, then there are four important properties proposed by Harder and Reuter back in 1983. The first one is called atomicity. It's all or nothing property. And then the second one is called consistency, meaning that whenever some transaction is applied, your state or your logic for your application should always be in a good or consistent state, or that some invariant that you want to maintain are always satisfied. And then the third one is dealing with concurrent transactions or concurrent operations. Even though database is like kind of designed to support concurrent operations, but that we want to have a notion of isolation, meaning that the concurrent operation, they don't interfere with each other. And then finally, of course, we want it to be durable because any kind of update or any kind of transaction, we don't want it to lose that kind of information. So it sounds very good, but unfortunately, in terms of reality, the definition is a bit vague, and then many different people debate what should be the correct definition of asset. And then many database say that okay, they are ASIC compliant, but that becomes more or less a marketing terms. And then in fact, lots of database, especially distributed database, they don't really achieve what they claim to provide. And then if you look at Jepson, he and his team does lots of kind of penetration tests or like stress testing of the database, and it's a very fun read. Okay, now let's look at each property in more detail. Atomicity. And then as we have already seen in many different terminologies, because a different community try to attack the problem or they come up with a similar terms, but usually they mean totally different things. So in terms of transaction or database, atomicity means all or nothing. But like if you look at distributed computing, or if you look at read or write data objects, actually when we say atomicity, actually it means that linearizability. Okay. But now since we talk about transaction, what does it mean by all or nothing? And then this is related to how I define the notion of transaction. So let's look at that in more detail. In terms of database primitive operation, I do read and write. How do I implement this reduce $3 from A's account? So what you do is that you read A's account as a kind of object, and then suppose it assigned to A. Then you say, okay, A has to be equal to A minus 3, and then you write back this A to A's account. So this thing is stored inside database, and then this A is kind of your temporary variable. And then for this add $3 to B's account is the same thing. You read something from database, and then you update your local variable, and then you write back to B's account. And then if like everything succeed, you will commit. If something goes wrong, then you will abort. So that's the whole point of transaction. It combines multiple operation or multiple access to the database. Then now let's look at what should we maintain in terms of a transaction. So the idea is that you don't want it to be in a partial state. So that it's possible if like this thing is completed, but like the other thing is not completed, then you will get 97, and then this is still 0. And then the next one, if this is completed, you will get $3 here and still 97. Okay. So like in terms of like the business logic of this application, you want either this state or this state. So if this state, it means that no operation has been committed, and then this state means that all operations have been committed. So you cannot be in between, but you could either fail or like abort a transaction, or you could commit a transaction. Okay, so that's the first thing we want from the transaction. And then the next thing is about consistency. So that for consistency actually means that completely different things in different community. And in transaction or database, it means that my state has to maintain some invariance, and it has to maintain it all the time. And for partitioning, so last time we talked about hashing, and then there's one particular way of doing hashing called consistent hashing. And then in terms of replication, when we talk about this concurrent object, consistency basically define a set of allowed execution. So for example, strong consistency, linearizability, all those kind of things. But here we talk about consistent state. So what that means actually that in terms of this A and B's account, then what kind of invariant we want to maintain. So if you remember, we want to maintain that the data I transfer is never in the some weird state that no one received that $3, right? So if you think about it, the way to define invariant is actually very simple. What you want to do is that the sum of these two numbers should always equal to 100, because that what no matter how much dollar I transfer from A to B, in this case we only transfer $3, but the sum of them will always be the same. And then that's what we mean by consistency in this small example. But of course, different application may require different properties and may require different invariant. So if you think about it, do you think it's a property of the database, or it's rather a property of the application? And then in fact, it's hardly a property of database. It really depends on your application semantics and your business logics, and then only the user knows the invariant. So it's really difficult to ask the database that I say that, hey, maintain whatever I need without really knowing what users have in mind. So here, just a quick example. So in suppose the user don't know how to use a database, and then the way it write transaction is write this transfer money into two transactions. Said I'm going to reduce $3 from A's account and I'm going to add $3 into B's account. So even though these two transactions are atomic, but that is still possible to cause some inconsistency, because it's possible that this transaction succeed and this transaction fail. Or it's also possible the other way around. So this transaction failed, the first transaction failed, but the second transaction succeed. So it really depends on the user to maintain this invariant. Okay, so that's one weird thing, to have consistency as your property of database. And then the next one is isolation. And then this is the only property that is dealing with a concurrent transaction. So remember, we're talking about database, and nowadays most of database are distributed. So it's highly likely that two user or multiple user are accessing the same data object at the same time. So suppose I have transaction 1, I have transaction 2, I have transaction 3. Then now we start to look something, this thing start to look like the read and write operation we have been dealing with, right? So we need to have an abstraction or a property that tell us that what are the allowable kind of execution. And then serializability. So usually textbook they define isolation as serializability because it's one of the most intuitive way. It's similar to sequential consistency or similar to linearizability. It always adds a total ordering, and then it always require the operation to satisfy the legal sequence. So what that means is that you again have this artificial sequence or artificial total ordering, and then you are going to map your transactions into a sequential event. So suppose this one goes to here, and then this one goes to here, and then this one go to here. Okay, so suppose this is transaction 1, this is transaction 2, and then this is transaction 3. Then what you are observing is that whatever transaction 2 does, it must observe the effect of transaction 1. And then transaction 3 must observe the effect of both transaction 1 and transaction 2, even though they are overlapping, but like they don't really interfere with each other. It's always like done, executed or committed sequentially. So that's the notion for isolation. So now let's look at a simple example. Suppose I have two transactions, they are concurrent. The first one is the same thing. I transfer $3 from A to B. And then this one is that I'm curious about A and B's total amount of money. So I'm going to read A's account and I'm going to read B's account, and I want to see that what happens if what's the sum of A and B. Okay. So if this database satisfy atomicity and also satisfy isolation, then what should this thing return? This thing should always return 100, because that suppose this is transaction 1, this is transaction 2. So in terms of serializability, like here, suppose this is transaction 1. Then transaction 2, it's either here or either here. But if you remember from consistency, we know that the sum of these two numbers should always be 100. But let's look at what happened if the database does not ensure isolation. So it's very possible that, okay, I already reduced $3 from A's account. So the number of A here is 97. But I have not execute this second line yet. And then I start to execute this one, and then this one, and then I return this one. So what I will get here is 97. And then for this one, because I have not transferred yet, so it's 0. And then return A plus B, which is 97. And then this will violate the isolation. Okay. So then the next thing is that isolation. Actually, there are tons of them. So even though serializability is one of the most common one, but it suffers lots of performance penalty, because I remember whenever you need to require something stronger, you have tons of coordination that you need to do. And then if you are interested in what kind of isolation level out there, again, this website by Jepson, it provides a very nice overview, and then it tells you that what kind of common isolation level are out there. And then again, the database, yeah, there are tons of isolation level, and some database claim them to achieve something, but sometimes they don't. So for example, Oracle actually provides this serializable isolation level, but if you look at the code, if you observe it, it actually only implements a snapshot isolation. So here's a lesson to you. If you are a practitioner, when you are using something, you better make sure that the implementation really implements something that you need and something you want. Okay, finally, durability, which is probably the most simple one to understand, is that once the effect of transaction that's it's already kind of applied or committed into your state, then the state should be there forever. Okay, so I don't want my transaction to be committed, but later on the database fail, and I come here, I couldn't get my data, or I see some inconsistent data. No, I don't want that. Okay, then if we are talking about a single database or single server, then usually what it means is that the data or the state is already written to the hard disk or the SSD or some write-ahead log. And then if we are talking about multiple nodes in terms of a distributed database, then that means that a set of nodes that have already doing this replication and then have already the up-to-date state. Okay, that's all I want to talk about today. First is that what is transaction? Why do we care about it? And then we also talk about the ACID properties, and then some of the critiques and some of the examples. Okay, that's all. Thank you.